Thank you. Thanks for the opportunity to speak. So NP problems, which are the focus today, are a class of decision problems, computational decision problems, where you're given an instance and you have to decide whether it's a yes instance or a no instance. The property of defining NP problems is that the yes instance should be efficiently certifiable. They should have certificates of size bounded by some polynomial function of the input length, and which are efficiently checkable, that is checkable in some polynomial time. And I'll give an example straight away if that's too abstract. NP-complete problems are problems which are in NP and which are hardest for this class. If you could solve any NP-complete problem efficiently, you could do so for all others in the class NP. So these are believed by most computer scientists not to be solvable in polynomial time. And this is the P not equal to NP conjecture you may have heard about. There's also a bolder hypothesis called the exponential-time hypothesis, which in various forms has been kicking around for a long time, but it's sort of in its modern form is due to Impagliazzo, Paturi, and Zane, which roughly speaking says that NP-complete problems require exponential time. So I'll give more concrete statements in a bit. OK, so here's an NP problem. In the subset sum problem, we're just given a list of integers, a1 through an. For concreteness, let's say they're each of some reasonable bit length, say order of n. And we're given some target value t. And our goal is just to decide whether there's some subset of these integers summing up to t. OK? So elementary arithmetic problem here. Why is this problem in NP? Well, the natural certificate to witness that this we have a yes instance is to just show us the set J, and then we can verify ourselves that this equality holds. On the other hand, finding J may be much harder. And the naive algorithm to just try all such J is exponential. It takes time roughly 2 to the n times some overhead for the additions. It's NP complete, so according to P not equal to NP, we can't have a time bound of some polynomial in n. And the ETH, which I have yet to state, goes further and actually rules out a 2 to the little o of n time algorithm. So rules out a sub-exponential time algorithm. But it's crucial to note that neither of these two hypotheses, says that you can't do anything clever. They both leave a fair amount of wiggle room for algorithm design. And I'm mostly a complexity person, but I want to present some algorithms in this talk and show you that there are simple and charming algorithms which achieve non-trivial speedups over random guessing, or over brute force search for solutions to these problems, and which are also either optimal or nearly optimal. So part of the purposes of this talk is to try to provoke you to wonder if you could do better. So for the subset sum problem, I want to present an algorithm from 1974 due to Horowitz and Sani. And it works as follows. First, let's take our list of integers and split them into 2 equal halves. We're going to do an exhaustive enumeration on each half and compute all possible subsums. Okay? Sum up all possible ways of adding a1 through an over 2. And let's let L be the list of all these 2 to the n over 2 possible values. And similarly for the right-hand side, we'll compute R. So we have these 2 lists of numbers. And now we're going to sort these numbers. This will help us in a bit. And finally, we'll check if our target value t is in the set sum L plus R. So clearly, t is in L plus R here, if and only if there was a solution to our original problem. And the claim, I haven't fleshed out exactly how to do these steps, but the claim is that each of these steps can be performed in essentially 2 to the n over 2 time with some polynomial overhead. For the first two, this is immediate. We're doing exhaustive enumeration over 2 to the n over 2 possibilities, and we're doing some arithmetic. For the sorting, we're sorting these very large lists of size 2 to the n over 2. But sorting is a nearly linear time operation in terms of the size of the list it's working on. So you basically get the same complexity. And finally, this last step is the only one where there's some slightly new idea needed. So this is the last step we're focusing on here. Now, I'm just going to pretend that these 2 lists of integers are the L and the R, and we're trying to tell whether some target value t, say 20, is in the sum of L plus R. So we're going to bring up two pointers. We're going to start this pointer A at the lowest element in L, and we'll start B at the highest element in R. Now, we really want to check whether there's any assignment of A up here and any assignment of B up here, down here, that would give the desired target. So that would be a quadratic time in the length of the two lists. But actually, because they're sorted, it turns out that you can proceed as follows. You can start with the pointers as follows. And currently, the candidate solution is too large. 22 is too big. So in this case, we're going to move B to the left. All right, now the candidate solution is too small, so we'll move A to the right. Too large, so we'll move B to the left. Too small, just right, and we found a solution. Okay, so these two pointers are making monotonic progress. So this is a linear time procedure, and you can convince yourself that it actually finds the target value if it exists. So in conclusion, we get essentially 2 to the n over 2 runtime over exhaustive for lists of size n, and this is actually a very meaningful gain over 2 to the n. It doubles the size of instances we can solve, and this is important in cryptographic settings. So there's a lot of cryptographic or attempts to break crypto systems that work on sort of similar principles. So it's a meaningful algorithm that gets used in various forms, and these ideas get used. And we don't know how to improve on it, except in special cases, like when the numbers are fairly small, or when we have randomly generated numbers, or other such special cases. On the other hand, we have no evidence from complexity theory that this 2 to the n over 2 should be optimal. So the exponential time hypothesis predicts there should be some 2 to the c times n here, which is like a barrier, but we really have no account of where that barrier should be. One route to progress on this problem is through a so-called k-sum problem, which I'll define next. The k-sum problem is defined with respect to some fixed parameter k. The input to this problem is k sets of integers, each set of size n, and again a target value t. And now we want to know whether t is in the set sum of a1 through ak. The best known algorithm essentially follows the ideas in the last algorithm. You split these things into two halves, and you do the same kind of exhaustive search on either side. So we've seen that this idea of splitting into two halves is very powerful, and it seems, on the face of it, it seems like you should be able to somehow extend these ideas to splitting into three pieces and hope to get some kind of improvement to 2 to the n over 3 in subset sum, or get something like n to the k over 3 here. No such luck as far as we know, and it really seems like it's either a major blind spot in our algorithmic toolkit, or there's some intrinsic limit there, but we don't. It's a mystery. So this is a statement about on the algorithmic side. If we could do better than this for the k-sum problem, we could apply this to subset sum, and via the NP completeness of this problem to other NP complete problems. So that's an algorithmic connection, and you can turn that around to a complexity theoretic or hardness connection, which would say that if you assume that subset sum is really hard, according to the ETH, that would imply that the k-sum problem is also somewhat hard. It would take time, at least for infinitely many values of k, it would take time n to the omega of k as k grows, as you vary the parameter. And note that this k-sum problem is a polynomial time solvable problem for any fixed k. And yet, we're able to somehow take information about the complexity of NP complete problems, which presumably take exponential time or some such, and actually translate that into usable information about the complexity of problems in P. So this kind of commerce between the two domains is, I think, quite interesting. And we now have many such connections between various concrete problems like k-sum and NP complete problems like subset sum. Here you can sort of think of k-sum as being like subset sum's baby brother, although the exact connection between their complexities is not fully understood. And I think there may exist other and hopefully deeper connections of this kind. So if there are any questions about this part, or if not, I will go on to talk about a second example, the k-satisfiability problem, equally famous and well studied. Here we again have a fixed parameter k defining the problem. Our input is a CNF formula, conjunctive normal form formula, or an AND of ORs, where each clause has length at most k. And we want to decide whether some assignment to the variables causes this formula to be true. This is sure. So a CNF is an AND of ORs, where each OR is an OR of variables or negated variables. Yeah. So this is the prototypical NP-complete problem. And so it was sort of natural to pose the exponential time hypothesis in terms of this problem as well. So here's one way you can state the ETH. It would say that for some sufficiently small delta, there's no algorithm for this 3-sat problem, where k equals 3, which runs in time 2 to the delta n, times some polynomial overhead in the size of the formula. So, the naive exhaustive search would take 2 to the n times size of phi, and this says you can't do too much better than that. But again, it doesn't specify what this delta should be. Okay, so that's the problem. And I'm going to describe an improved algorithm for this problem. And this is going to be a randomized algorithm. It's going to have as its core component, not an exponential time algorithm, but actually a polynomial time algorithm for this problem. The catch is that this polynomial time algorithm is going to fail most of the time. What it's going to try to do is, given a formula phi, it's going to try to randomly guess a satisfying assignment to phi. And the hope is that it can do so with some non-trivial advantage over random guessing, which would give you a success probability 2 to the minus n, in the worst case. So this says, this result of PPZ says that there's some fast algorithm that if you give it a satisfiable phi on n variables, it attains essentially a 2 to the n over k advantage over random guessing. So it's that much more likely than random guessing to succeed. And now, this is a polynomial time algorithm, but you can just run it many times. You can run it for this many trials to obtain a solution with high probability if one exists. And if you didn't find one, you can say, well, it's probably not satisfiable. Okay. And so for any constant k, this is a polynomial, well, it's an improvement in the exponent for this exponential factor. Now, an interesting fact observed by Paturi and Pudlak is that many of the improved algorithms that we have for all sorts of NP-complete problems actually have this form of intelligent random guessing. Or if they don't, they can at least sort of be massaged into that form. You can get an equivalent algorithm that has this format. And I think this is a rich and natural paradigm for algorithm design. It doesn't seem to express all the ideas we have about solving NP-complete problems, but it expresses at least many of them. And so from a complexity perspective, I'm interested in understanding the limits of this paradigm. I'll get back to that. But let me describe an algorithm within this paradigm, this PPZ algorithm. So we're given a formula phi, and we're going to try to assign x1 through xn to satisfy it. And the algorithm is very simple. First, we're going to randomly reorder the variables. Okay? And then we're going to go through the variables in that order, and we're going to set them one by one. And there's some notion of criticality. So at each stage, we've gone to the ith stage, and we want to set this variable x sub sigma I. And basically what this says is, if there's some obvious reason you should set it to 1 or to 0, then do so. If you can't see an obvious reason, then just set it randomly. And I'll explain by example what it means for this variable to be critical. So here's an example. Let's say our algorithm first picks x2 as the first variable to be fixed. Well, x2 is not critical, so we're going to fix it randomly. Say we fix it to 1. Now, this term is satisfied by the 1, so we can just simplify. This term is not satisfied by this. This clause is not satisfied by this term, so we'll remove it, and we've simplified to this. Now let's say we randomly choose x3 as our next variable to be fixed. Well, x3 is the only term here, the only term left over here, and it's responsible for satisfying this clause. If we set it to 0, we're finished. So instead of setting it randomly, we'll set it to 1. All right, and now the entire formula is satisfied, luckily. And so the claim of these authors is that this very simple approach actually has this non-trivial advantage. And I guess the very rough idea is that you hope to get many of these critical variables where you don't have to make a random choice, but your choice is forced on you by past choices. And that reduces the amount of uncertainty that you have as you form this solution. So I want to talk about limits to these intelligent guessing procedures. These are one way of designing exponential or improved algorithms for NP problems. Very straightforwardly, we can say that the exponential time hypothesis implies that no polynomial time procedure can solve satisfiable 3 instances with success probability 2 to the minus little o of n. If it could, you could just repeat it 2 to the little o of n times and get and solve the problem outright. But this exponential time hypothesis, as I'm sure you can tell, is a very strong assumption. So whenever possible, we'd like to base our understanding of the limits of algorithms on the weakest possible assumptions. And in fact, for these particular class of algorithms, based on this intelligent random guessing paradigm, we can prove better limits under weaker assumptions. So first, Paturi and Pudlock proved in their paper that for a problem harder than KSAT, called circuit SAT, if you could even do slightly better than random guessing, say 2 to the minus 0.9n, or 2 to the minus 1 minus epsilon times n, then not only would circuit SAT have algorithms with runtime 2 to the 0.9n, which is obvious, but actually they would have algorithms of time 2 to the n to the 0.99. So a more radical exponential improvement than you would naively expect. So this is quite I think a surprising and interesting result. There's a catch that circuit SAT is a harder problem, and that these algorithms are non-uniform. But it's the kind of the flavor of what I was asking for.
So the conclusion algorithm is not random, or it's not probabilistic.
Well, they use non-uniformity, so you can non-uniformly fix the random bits in some way that is good for your purposes. So non-uniform algorithms basically give them, for every input length, they give themselves some advice that's determined in some non-constructive way. And in particular, what you can do is you can pick a setting to any random bits you might want to use that's good enough for all the inputs of length n. So in this non-uniform setting, randomness can be eliminated. It's a general principle, but yeah, they also have some results about the uniform setting, but they would use randomness. And I was inspired by their work and wanted to study this issue further. And so earlier this year, I proved that there's some kind of a similar statement for 3-SAT, an easier problem than circuit SAT. I say, well, suppose you could get a polynomial time random guessing procedure, like the one we saw, that got success probability, say, 2 to the minus n to the 0.9, or something less than 1 up here. So I'm asking for a better advantage over random guessing than their result asks for. But I'm only asking for this better advantage on an easier problem, the 3-SAT problem. And the conclusion that I draw from this, the presumably unlikely conclusion that I draw from this, is I think is even more unlikely than this, I believe. So the conclusion is that if this were possible, and I think it's not, then this unlikely thing would occur. NP is in co-NP poly. And roughly speaking, this would mean that Boolean, say, tautologies in propositional logic could be proved by some kind of proof system that for a tautology of some length n would give you a proof of size polynomial in n. So it would be sort of a super efficient proof system. And we have no reason to believe that these exist today. Okay, so that's what has happened for these intelligent guessing procedures. This is one paradigm for exponential time or improved NP algorithm design. But there are others out there. And I think that using maybe some of the ideas developed in this work, we can move on to show that other restricted paradigms of computing are weak for NP-complete problems. And one conspicuous candidate is algorithms that have a superpolynomial time budget, but have only a polynomially bounded space or memory usage budget. It's very, when you're designing exponential time algorithms, they may be practical, but often the bottleneck is the space usage. And this is a practical interest, but also I think space bounds on computation tend to be very useful in analyses of computational classes. So this would be a candidate to study next. And one of the problems that's been identified in this area is, we saw an exponential time, exponential space algorithm for subset sum. But what if you wanted to hold yourself to polynomial space? Could you even do slightly better than the naive 2 to the n? This has been open for, well, since the 70s. So that's all I had to say, but thank you.
Thank you very much.